Okay, today is lecture 12. I'm not sure this not today is the last lecture in November, but this will be not the last lecture. Probably so today then will be 6th of December and about 13th of December. I'm not sure. So it remains either 2 or 3 lectures. It depends how it will go with materials and how many resources we have for the further stuff. Okay, and today, so I'm going to start to talk about the last huge topic which I plan to cover in lectures. It is a cluster structure for the space of local systems. Okay, just local systems. But before, let me, for the motivation, recall something which was discussed on the first lecture. So believe me or not, these are the slides from the very first lecture, preliminary examples. And on this very first lecture, we discussed the following example, which is configuration of points on P1. We take n distant points on P1, modulo the action of PGL2, which I denote by U1, UN, and we assign them to the vertices of the n-gon. And then if we take any triangulation of this n-gon, we can assign certain coordinates, namely cross ratio corresponding to each diagonal in this n-gon. And this cross ratio, in this picture, we have 3 cross ratios. They are coordinates on the configurations, in this case, of 6 points on P1. There was a problem that if we change triangulation, then the transformation is given by the following formula, in which we can now recognize mutation of x variables. There were some misprints, typos in the original text, but probably some people follow disagreements on convention. Now I believe it is correct, and probably it's like this, but who knows. Quiver is not written here, but quiver is standard for any triangulation. We draw like this, and I will do this again. So the question from which we start. So we know coordinates and actually cluster coordinates. Right, x. Configurations and point in P1. Geometrically, this corresponds to triangulations of n-gon, or a bit more topological, if you want. It is what is actually important for us is the cyclic order on this n flags only this n points on P1. So flags that we draw, there's some n-gon, so these are straight lines. This is not important, and even fact that these are lines not important. So geometrically, instead of this, you can think that you have disk with I don't know what is my favorite color for marked points. Let me use this color. We have disk with n marked points. On the boundary. And for each marked point pi, we assign ui, which is a point of projective line. And of course, we use this assignment model the action of the group, which is in this case PGL2, the group which acts on the projective line. Okay, this is what we know. A question. Can we consider more general surfaces? So in the example above, as a surface, we have disk or polygon topologically it is equivalent. One can ask for surface with I don't know, with more punctures, handles, holes, whatever. Let us try. So let S be a surface with punctures. And it is sometimes it is convenient to work with to assume that surface can have boundary. For example, here you see we actually have boundary. So probably with boundary and marked points. We made some assumptions in order to have this approach work. So we assume that any boundary component. Let me move this over to the next page. Any boundary component have at least one marked point, and overall number of marked points and number of punctures is greater than or equal than 1. And maybe I also assume that any characteristic of the surface is negative. So I excluded a sphere with one puncture, sphere with two punctures, and sphere, yes, sphere with one and two punctures. So I want to, starting from the surface, So this is a generalization of the disk. To do something like that. Let me denote by S tilde as hat maybe. B universal cover. Construction here, construction of the coordinates started from triangulation. So triangulation. So here, let us pick some triangulation of the surface. What kind of triangulation we will consider? I'm trying to say that everything is similar to what we have for the disk. So we have triangulation. I assume that the vertices in marked points and punctures, in special points which we have in our surface. Example. So the simplest example is probably torus with one puncture. Here is a puncture. And we have two triangles. They share the same vertex. We have only one vertex, but still. You see that. I mean, in this case, we have almost no other choices. But so this is torus. For example, A, which is torus is one puncture. Example B of the same spirit will be sphere with 4 punctures. For sphere with 4 punctures, maybe the simplest way to write is the following. This is actually some sort of tetrahedron, which is topological equivalent to sphere. Okay, we can lift this triangulation on the universal cover. Universal cover I denoted by S hat. Maybe later I will change notation. Think a bit more. Now, the next, probably more or less the last step, we should assume that we have here we that here in each marked point we had a line pointing to P1. So assume that we have a map from vertices of triangulation to P1. But for the reason which will be clear in a minute, I assume that this map goes not from vertices of the triangulation of S, but from the vertices of the triangulation of S hat. Then we can, and such that. Okay, let me say from the beginning what is the condition. Such that corresponding, such that coordinates corresponding to edges of triangulation are pi1 of S equivalent. What do I mean here? That if for any edge which we have in our triangulation, any edge can be viewed as diagonal in some in some foregone, and we have formula. Maybe in order to avoid some further confusions, this is not possible. Okay, in order to avoid some further confusions, let me copy this convention which I had in the first lecture and adapt it here. So what does it mean? That if we have if for foregone and like here, okay, let me here in the example we have diagonal from 2 to 4. Let me draw the same diagonal here. And says that here we have U1, U2, U3, U4. Then the value of the corresponding variable which is assigned to the vertex will be, according to this convention, U1, U2, U3, U4. If we have assigned variables, we assign points in P1 to each vertex of the triangulation, then for each foregone, we can compute the corresponding cross ratio. So we have assigned some number, some coordinates to each edge. And I assume this condition means that actually the variables are assigned to edges on the original triangulation. So hence we have a map which goes from edges on original surface. Лекция. У меня сейчас лекция. Извините. Sorry. Can you still hear me?
Yes.
Yes.
Okay. We have a map from edges on C to C star to C. Actually, the conditions that map X on C actually assume here. I actually assume that all my flags, all my points P1 are different. I will come back to this assumption of a bit later. This is just some sort of assumption that everything in general position. So maybe I want to support what's going on by some picture. So we have some triangulation. The picture will be rather abstract. I don't mean to. Here I wrote rather concrete torus, sphere with number of functions. Here I will be rather abstract. We have some triangulation. This triangulation lives on universal cover, and there is a map from universal cover to our original surface S. And this map is a quotient by the fundamental group which acts here. So for each triangle here, we can have many pre-images. I don't know how to write it. It is here. It can have several pre-images here, and they are connected by the action of the fundamental. Okay. I assume that for example, this fundamental group can map, for example, this foregone maps to this foregone, and I do not assume that all the corresponding flags coincide, but I assume that there is a map. So we have a map from for any element, for any gamma from P and S, we have rho of gamma which belongs to PGL2. And if we act by gamma on the surface on the universal cover, P1 of S acts on the universal cover, then the corresponding flags, so this map I will denote by U. Then we have a map from then the corresponding U's are transformed by the action of this rho of gamma. Okay. Maybe okay. Let me explain it again in the opposite direction. On the opposite. Assume that we indeed have a weights assigned to each edge, similar as we had in the case with triangulation, similar for n equal 1. For the case with this with mark point, assume we have a map this map I denote by x. AX edges on S to general C star. Then we can, if we start from take some triangle. Using our group GL2, we can assume we can assign points infinity -1 and 0 to each to its vertices. PGL2 acts freely transitive on the set of three on configuration of 3 different points. So using PGL2, we can send one of them to 0, another to infinity, another to -1. And if we have force points, this here cross ratio comes. Then now with using H weights, we can compute other points, we can compute, let me denote the letter, we can compute U. What do I mean? I mean that if we know values u1, u2, u3 on some triangle, and we know the value of the corresponding x here, then we can compute I don't know how to write it. Okay. Then we can compute this u4 because there's only one point such that the corresponding cross ratio will be equal to x. Then look into the next triangle. We can compute u5 and so on. So if we know h, the weights assigned to h's, then we can compute all then this is an inverse map. Then we can compute all points, compute map u, all lines assigned to vertices. There is some gauge freedom which can be fixed, saying that this 3 for given triangle we have -1, infinity, and 0, and everything else can be computed uniquely. Okay. But here you can see the difference between S and S hat. For S hat, you just start and go, and you can come to any triangle, and everything is okay. But for S, you can go through a certain line and return to the same triangle from which you started. Or you can have different not homotopic passes from one triangle to another. It means that generally speaking, if you for S, it is possible that you don't have this canonically defined map U from vertices to the P. On the contrary, if you go through through some path on S or equivalent to some so in S it is loop, for on S hat it is a path. You come to triangle, but with different points on P1. So you can for any gamma P1 at S, if you go by gamma, you obtain the same triangle, but in principle with now other another U1, U2, U3. And there is a unique element in the group PGL2, just unique rod gamma belongs PGL2, such that rho gamma of infinity is equal to 1, rho gamma of -1 is equal to 2, rho gamma 0 is equal to 0. So hence, we obtained a representation of the fundamental group in PGL2. Let me summarize what we stated now, and then we'll discuss it again. So we have C star in power number of edges, and we have a map actually in both directions from this from C star number of edges. This map, you can see, is actually rational. To what? To the homomorphisms from fundamental group of surface to PGL2. This quotient by the adjoint action of PGL2. But actually, we have some additional data. And this additional data is related to these lines which we fixed from the very beginning. If you just go around some point, if you have some point, let me draw it as a puncture, and you have some path. Puncture this, and you have some path. Or maybe some path around it, gamma. So you start from 3 lines here, and using coordinates which you assign to each edge, you find a line here, a line here, a line here, a line here. You find all lines. But we start from some point. So we have P is a puncture. Let P be a puncture. And let gamma be a path. Actually loop around P. Then, if we take this row of gamma and apply it to the line assigned to P, then you see that this is equal to UP itself. Because when we go in this direction, we recompute all other flag lines, but line assigned to point P remains intact. So this is this additional condition. Let me put it before this, after this observation. So I need. So we also picked invariant line in each punch. And by definition, this is called framed PGL2 local systems. Yes. So we found some coordinates on the frame PGL2 local systems. We don't, in the example which we had in the very beginning, which correspond to the disk, we don't have this story about PGL2 because this is already self-connect, so we don't have any monod. But if you try to do something more involved, like here maybe I should draw that I assume blue, like torus or sphere with sphere, then you naturally come to the representation of the fundamental group, which is by definition. The word local system should resemble the following. I don't know, again, some picture. So we have our surface. Let me now draw it. As it has some handles and some punctures. Maybe I can draw punctures with the same color. No need to. And we have more correct to say we have principal PGL2 bundle with flat connection. So it means that for any point we have a group, maybe some other color. Sorry, I have many colors. It took me some time to pick one. And for any point, we have a group, and we have a flat connection, which means that we can, for any pass on the surface, we can move up and have a pass on our bundle. But if we go by some connection flats, local transformation of this pass do not affect anything. But if we, globally, yes. But if you have some path which is not contractible, then it can give us some monodromy on the on our bundle, and this is monodromy of this connection. Maybe I should. I didn't make it clear. So this quotient. So here is a quotient. We should take the quotient by the joint action of PGL2. Here it means the following: so even if you fix the initial point, you don't have identification of the fiber with PGL2. You need to specify a point which corresponds to identity. And if you change this point, this leads to the conjugation of the monodromy. And here is the same. I started for some triangle for which I assumed, okay, let us say things here 0, -1, infinity. Maybe it will be more clear if I write here that this is U1, this is U2, this is U3, and this will be primes. And our element just maps them to primes. But anyway, this is just notations. I mean that I here started from certain triangle. If I started from other triangle, then I can obtain another representation of the another monogram, another matrix formally. So everything is defined up to this conjugation. Okay. Maybe we have let us just a bit look on some example. Okay, example A will be the same as above with the torus with one function. If you think about the torus topologically, then its fundamental group is generated by two passes. One say A, and another is B. So in this case, fundamental group is F2 free group generated by, let me write gamma A, gamma B, in the sense that A and B are elements of the homology. I took certain representatives. And we don't have any condition on them. So if we consider homomorphism of pi1 of S PGL2 modulo PGL2, then what is the dimension of this space? So we have to specify two matrices. Oh, it's element of PGL2, so this is not literally matrix. It is a matrix modulo -1, but for the dimensional counting, this is not important. We have to specify two matrices corresponding to A, gamma A and gamma B, and take the quotient with respect to PGL2, which is PGL2. So what is the dimension? Who can compute?
Seems like 4, but I'm not sure.
How did you get this for?
I thought to diagonalize one matrix if in generic case.
Yes, it's in
Then
case.
second should commute with it. And
why? Sorry, why it should commute?
I thought we want torus, so
yes, but this is a torus with function.
Sorry, if it is free group, then the second can be anything. Then okay. I think then it is like 2 plus 3, so 5.
Too much. we have two matrices, row of gamma A, row of gamma B. Each of them belongs to PGL2, so it has 3 coordinates. And we have, so overall, the space of this homomorphism is 6-dimensional. And we take the quotient with respect to 3-dimensional group. So dimension is equal to 3. And this is exactly equal to number of edges. Which is okay because my main proposal was that we have a map which is rational, and so this is accord. Of course, you can ask, can this can be made more explicit, more how to write down everything's coordinates, and explicit way to do this, I put it as a problem. So write representation corresponding to, for example, if we take this this triangulation and put weights x, y, z. But I will comment a bit how to make this, how to give some hints and so on to this problem. But this construction, which I mentioned implicitly, says that for if you know this x, y, and z, then you can write two matrices which correspond to gamma A and gamma B quite explicitly. This x, y, and z, there is a map from. You can parameterize these triples of pairs of matrices. Okay, maybe I can comment. Okay, let us look at, to example B. Okay, S2 is for punctures. In this case, what is a fundamental group? So a fundamental group is generated by 4 matrices, M1, M2, M3, M4, which correspond to the passes around any of these punctures, which are subject of relations. The product is equal to 1. And let us again compute the dimension of the space of homomorphisms. Who can? So homomorphism. Yes.
Is this 6?
Yes, this is 6. And how did you get this 6?
Well, we have one matrix is defined uniquely by the rest of matrices, to say M4. Then we have free space of free matrices. Each matrix gives dimension 3, and then we should factor by free action, which should give us substitution of 3 from 3 by 3, 9.
Yes, exactly. And again, this is just the number of edges, which one can easily see. So in principle, this is just more like illustration. Here I try to explain that I constructed maps in both directions. If I know the edge weights, and I can construct the homomorphism, and on the opposite direction, if I know this invariant lines and homomorphisms, then I can construct this map U on the universal cover and construct the edge weights. So in principle, we have one-to-one correspondence for generic positions. So therefore, the dimensions should coincide. But maybe it's hard to follow whether it's proof or just speculation. And this example can support. Okay, remark. Actually, the space of the framed local systems form not a manifold, but even a stack. In order to avoid this words, and we work on open subset where everything is in general position. For example, when I said that the map X maps to C star, I assume that some points are different when we compute this. In order to this do not equal to 0 infinity, we need to assume that U1 is different from U2, U2 from U3, U3 from U4, U4 from U1. Otherwise, we have problems. So, and for PGL2 case, I think this is the only assumption which we actually have. For high rank, assumption will be more delicate. Okay. Okay. Let me do some more computations. How to construct what I'm going to say is that actually this monodromy can be computed more or less as a product of two types of matrices. So first, we two transformations. First, if we have some triangle, we can always assume that corresponding cross sections here, corresponding lines here correspond to 0, -1, and infinity. But when I draw some path on my surface, yes, or on the universal cover, it is for identification, I should come to not just to this triangle, but this triangle with the same order of the vertices. So one of the important transformations is rotation. So we have transformation. Like this. And it is given by matrix. The corresponding matrix G is equal to, let me look to my notes. I hope I computed it before. -1, -1, 1, 0. So it maps. So I assume that here, when I write Z, it corresponds to the vector Z1 plus E2. So the 0 corresponds to the second basic vector E2. Could it be so? Yes, could be so. And infinity corresponds to the first basic vector E1. So this G it maps E1 to minus E1 plus E2. E2 maps to minus E1 and minus E1 plus E2 maps to something. But only lines are important for us. Here also line. So this is. So if we have some path on our surface and return to our triangle, and then need to rotate it, then we have to apply this matrix. It is easy to see. Note that this matrix is actually identity. So if we rotate 3 times, we get. Of course, this is clear from our motivation to introduce this. Okay, 1. And second transformation which we will need is how to pass from one triangle to another triangle. So assume that we have 2 triangles. And I assume that assume, what's my convention? Let me look again. Assume that the corresponding points in P1 are as follows: infinity, -1, 0, and z. Then the corresponding variable here, maybe in one convention, will be z inverse. Then if you look to so how to what's going on, we should go from this triangle to this. So we can look at them as follows. I just move them away. So here we have 0, in this triangle, and we can take a matrix of the form maybe like this, not for sure. So it maps E1 to E2, E2 to E1, and it maps minus E1 plus E2 to E1 plus E2. Maybe like this. So it maps this. So it maps this vertex to here, this to here, and this to here. We cannot just map -1 to z because this will change our rotation. So we map this vertex to here and permute other two. Anyway, so this G corresponds to the path from one triangle to the neighbor one, and this G corresponds to rotation, and any monodromy can be expressed through this pair of matrices. This is how it goes. Let me state one more property of this construction. Show for any function me draw the picture of this puncture. And assume that let me also write weights of the edges which are adjacent to this function: x1, x2, xk. And assume that we take the path gamma, which goes around this puncture. For any puncture, let me write it, say it in the opposite direction. Let P be a puncture, gamma pass around it, and x1 k weights of edges adjacent to P. Then, if we compute rho of gamma, then its eigenvalues are like 1 and x1, xk. So maybe I should know that this is in PGL2. It means that if we have matrices in PGL2, then you can multiply it by any scalar, and all the eigenvalues will be multiplied by its scalar. So only ratio of eigenvalues has meaning. In other words, that the ratio of eigenvalues of this matrix around this point is equal to the product of the x variables which we have here. Okay. Maybe one more remark to change transfer flip of triangulation. Correspond to mutation of variables. And this is actually the problem which we had in first lecture. Since x variables are defined on the universal cover, so there is no issue of monodromy. So this is just local computation. So the computation remains the same. Maybe the only thing which we didn't mention in the first lecture, and I have to say explicitly now, it's a quiver, and the quiver is constructed by the same way as we did for Grassmann and for many other things. We, in each triangle, we draw arrows which connect edges and orient them clockwise. Okay. Okay. I don't know. I have 10 minutes. Was it good to start new topic? But let me at least. But let me start but slowly. So, so question. Higher rank generalization. So all of that was about some cluster coordinates for PGL2 local systems. What? So PGLM local framed local systems. And the first question is, what do you mean? What do we mean by frame? And partial. There are okay, and here I for each function and mark point I assign a line, but actually maybe you heard several times I missed this word line with the word flag. So definition. Definition. And maybe I write the names. XGS is a space of G local systems plus choice of invariant flag for each marked point puncture modular equivalence. By equivalence, I mean there is an action of PGLM. So now so this is a general definition, but here we have G is equal to PGLM. And next time we will discuss cluster coordinates on the space of XGS of the local systems. Okay, I think it's a bit better to stop today, but probably next time we'll say that I will need 2 lectures, not 1. But anyway, let me stop today. Are there any questions?
Can we have some generalizations such that even in case of rank 2 or maybe not 2 in case of PGL2 or in which we will assign some additional data like for Riemann-Hilbert problems when we have some asymptotical data in at each puncture.
Asymptotical data, you mean like for solution of linear differential equation?
Yes. I mean that we have connection, and here also we should have probably connection up to some gauge.
Here we have this. Here we live on the monodromy side. So we have exponent of this behavior, but we don't have this logarithm.
But if we have two connections with the same monodromy, in this case, it would be true that they are gauge equivalent.
They will be equivalent by Backlund transformation, yes. There are Backlund transformation which shift parameters by integer sum, and they connect different asymptotic behavior near punctures.
Okay. Okay, thank you.